I guess we're about to start. So today's is the assessment of spectral attributes in identifying gas hydrates and seismic data from Pegasus Basin offshore New Zealand. Emily Jackson is the master's student. This is her thesis. A week from today, we have Ryan Pastor, and his title is Effective Replacement for Cyanide in the Leaching of Low-grade gold ores using thiosulfates. So,
right.
Ryan, thank you. And Emily, I'm going to go ahead and let you start. You can give a little bit of background of yourself, and then we'll go from there. How's that?
Well, thank you so much, Doug, for the introduction, and thank you for having me talk to you guys today. I'm excited to give you this talk. And yeah, I'll start off with a little bit about me. I have a bachelor's in geology, graduated in 2017, and then right away I went to work as a staff geologist in Baltimore, Maryland, for a little geotechnical company. Did a lot of field work, which was fun, being outdoors, learning about different construction materials, but wasn't really super passionate about that job, and I wanted to be a grad student for a while, so I decided to go to grad school. I have a master's in geology from West Virginia University, and I was really involved with AAPG there. And it was at WVU that I discovered geophysics, and that seismic interpretation was really interesting to me. So I came out here to OU and started studying gas hydrates, and here I've been really involved with AAPG and SEG. And what I'm going to present today is some of my work on gas hydrates. So my presentation today will start with just an executive summary to give you a high-level view of where this talk is going, and then the project background, my geologic settings, and previous work, the data set that I have. And then I'll go into the workflow and methods before talking about the results and discussion. Then I'll have some conclusions at the very end. So first of all, though, the executive summary. Well, gas hydrates are a solid crystalline structure of methane gas that's been trapped inside water molecules. And these can pose concerns for engineering, drilling through gas hydrates, climate, seafloor instability, if hydrates are released really rapidly. And within seismic data, hydrates are commonly identified by this seismic anomaly reflector that we call a bottom simulating reflector. And I'll talk about this a little bit more in a minute. But when we have BSRs, they're a really good indicator that hydrates are present, but they are oftentimes missing, and they cannot accurately predict the concentration of gas hydrates in the subsurface. So other methods are needed to identify gas hydrates when BSRs are absent or data scarcity exists. So the deliverables for my project are to assess spectral attributes, ability to measure attenuation in gas hydrates, and then to implement machine learning to enhance attenuation-related variations in the gas hydrate stability zone. The main takeaways, which I'll discuss a little bit later, are that spectral attributes proved useful for identifying attenuation or zones of attenuation within the gas hydrate stability zone, and then machine learning proved to be useful for enhancing attenuation and amplitude-related variations in my seismic survey. So gas hydrates were first discovered in 1810 by Sir Humphrey Davy, but it wasn't until over 100 years later that their importance was really recognized. And in the 1930s, they were observed to be plugging natural gas pipelines. And so after that discovery, there were a few decades of research on the crystal structure, chemical properties, phase equilibrium, thermodynamics, and different features of gas hydrates. In the 1970s and the 1990s, there were a couple important gas hydrate discoveries at the Blake Ridge, which is offshore the Carolinas, Georgia, along the US East Coast. And then the Malik wells were drilled in the Mackenzie Delta, Northwest Territories of Canada. And there have been quite a few studies on both of these areas, in addition to the Gulf of Mexico hydrates and some hydrates off of Japan. Then in the last 2 decades, there have been numerous laboratory, well, seismic, and synthetic studies on gas hydrates and hydrate-related BSRs, attenuation, velocity fluctuations, and things like that. So my research is building on what's been done before and attempts to answer 2 main questions. The first is, can skewness and kurtosis measure attenuation within the gas hydrate stability zone? And if these attributes are useful for measuring attenuation, can we use them as a type of hydrate indicator, similar to how many seismic attributes are used as direct hydrocarbon indicators, or DHIs? The second question is, can machine learning enhance attenuation-related responses in the gas hydrate stability zone using these spectral attributes and some other more classical attributes like RMS amplitude? So a little bit just about gas hydrates in general, in case you're not familiar with them. I didn't really know about gas hydrates until I started at OU less than 2 years ago, but they're super fascinating, and they occur primarily in shallow ocean basins or in permafrost settings in more polar regions. Global estimates for gas hydrates are around 250,000 trillion cubic feet, which is almost 90 times more than the amount of natural gas estimates for the US. So there's a significant amount of methane trapped in these gas hydrates. Hydrates occur in the subsurface in the gas hydrate stability zone. This is a theoretical zone that is dependent on temperature and pressure, often pressures and low temperatures. Within seismic data, we have hydrates. The top of the gas hydrate stability zone is determined by the ocean bottom. So this is from the Blake Ridge offshore east coast of the US. So we have ocean bottom. So all of this is just water column. And then this seismic reflector here is the BSR. So between these 2 key seismic horizons, this is the theoretical zone where we would expect hydrates to occur. Now, it's important to keep in mind that we might not have hydrates throughout this entire zone. We might have hydrates in thin layers throughout the gas hydrate stability zone, but based on those temperature and pressure constraints that determine where hydrates can exist, this is where we could expect to find them. Now, hydrates can often act as a seal or a trap, similar to like a shale would trap hydrocarbons. And often we see trapped free gas below gas hydrates. And it's the contrast between hydrates and the trapped free gas that gives us this strong BSR reflector. So where we have BSRs, they indicate the base of hydrates, and they're easily observed in seismic data when they cross-cut stratigraphy. So that's a little summary on gas hydrates and BSRs. Now, as I mentioned, we don't often have BSRs, or they're sometimes very weak, or they just don't show up very well in the seismic data. So in that case, we need other methods to identify hydrates, and that's where attenuation comes in. So attenuation is energy loss, and it results in reduction of seismic amplitudes. Attenuation has truly proven to be quite complex, and the exact mechanism of attenuation is not entirely well understood within gas hydrates, although there are a plethora of studies that show attenuation within hydrates. So what is known is that for hydrate-bearing sediment, with increasing hydrate saturation, we have a decrease in porosity and an increase in velocity, both VP and VS. Subsequently, we see an increase of attenuation, or attenuation is increasing, and that can be observed on the seismic wavelet, with those amplitudes being reduced in zones that have hydrates compared to zones that don't have hydrates. And we can also see the impact of attenuation on the seismic spectrum. Here is a spectrum that has not been attenuated, and then the dashed line represents a spectrum that has been attenuated. So you can see reduction of amplitudes, especially in higher frequencies. We've observed that there's a somewhat frequency dependent component of attenuation in hydrates. So some mechanisms that have been proposed to address attenuation within gas hydrates are macroscopic fluid flow, squirt flow, and patchy saturation. And I won't get into these too much, but basically they are just ways to explain how we get this energy loss in gas hydrates. So based on results from many different studies, many different papers I've read to try to understand this attenuation, the expected result is an increase in attenuation or increase in energy loss in gas hydrate saturated intervals. So then how do we propose to measure attenuation since we don't have well data, or if we don't have well data? Well, we measure attenuation then on the seismic spectrum, and there are two different attributes that we're proposing to use to measure attenuation. Now, seismic attributes are just mathematics that we apply to enhance a feature within our seismic data. So it's not magic, it's just math that we apply to seismic. And the first attribute is skewness. Skewness defines a data set's deviation from the normal or Gaussian distribution, and it's a spectral shape attribute, so it measures the change of the shape of our seismic spectrum. And if our data is positive skewed, that means most of the data is skewed toward the left, or its tail is weighted toward the right. And negative skewness means that most of the data is skewed toward the right, or its tail is weighted toward the left. Kurtosis, on the other hand, defines the number of outliers or weight of the tails, which determine whether kurtosis is positive or negative. So if you have very few outliers and maybe a very broad spectrum, then you would have negative kurtosis. And for positive kurtosis, you could think of this as having maybe a few peaks in your data and then very many outliers adjacent to that, and that would give you positive kurtosis. In general, what we see is that seismic data is not normal. It doesn't have a Gaussian distribution normally. We see positive skewness with more lower frequencies in seismic than higher frequencies. It's pretty typical. And then for my data, I've observed that it's mainly negative kurtosis. And what we expect attenuation to do is to increase our positive skewness. So data will become increasingly positive skew and increasingly positive kurtosis as well. Okay, so now some background, a little more geology of the area. My data is located in the Pegasus Basin. So these are the North and South Islands of New Zealand. This is where the Pacific plate is being subducted under the Australian plate, and the Pegasus Basin is formed along that subduction zone and the ancient margin of Gondwana here, which is the Chatham Rise. So if we take a look at a cross-section across this area, we see the Pegasus Basin located right here, and gas hydrates are expected to occur within the shallowest portion of our data set. Well, unfortunately, there have not been any wells that were drilled within the Pegasus Basin, so we have to make correlations to the nearby East Coast Basin here, or surrounding areas that have recovered, that have drilled into these areas. Hydrates occur, as I mentioned, in the very shallow subsurface of the Pegasus Basin, and these are primarily Pleistocene in age, although the entire Pegasus Basin is Miocene to Pleistocene. So from the nearby locations, such as the East Coast Basin, these sediments within the Pegasus Basin are interpreted to be mixed siliciclastics from turbidite or fan delta deposits. There have been previous studies on the Pegasus Basin by OU alumni to researchers specifically that graduated before me in my research group, and specifically two studies on attenuation or BSRs. So the first study in Claremont et al. Estimated attenuation using Q, which is the quality factor, its inverse attenuation. And for his research, he showed that high Q, which are these orange colors, and then low Q or low attenuation are the blue colors, corresponded to this high amplitude BSR in the Pegasus Basin. So here's the BSR, this is the ocean bottom. And the high attenuation below the BSR is likely due to methane gas accumulation. And then above the BSR, This is likely due to gas hydrate accumulation within the gas hydrate stability zone. Another study on the Pegasus Basin used seismic attributes and machine learning to enhance this weak BSR throughout the central part of the basin. So both of these studies were very useful for me to show what had been done before in the same setting and what had been proven useful to enhance attenuation or BSRs. Excuse me. My seismic data set is the APB 13 2D seismic survey. And this was acquired in 2011 by Anadarko, New Zealand. It consists of 52 2D seismic lines that cover about 4,400 kilometers of data. And I have access to the full, near, and far angle stacks, which I utilize for my research. And although I don't have access to well data, since there aren't wells in the Pegasus Basin, there have been methane hydrates recovered from drop cores by a scientific cruise completed in 2014. So this is my data, the APB 13 seismic survey, and taking a look at the gas hydrate stability zone within this data, we have the top defined by the ocean bottom, and then we see this really nice BSR here, what I call a strong or high amplitude BSR, and then here the BSR is very weak or low amplitude. So that's the base of the gas hydrate stability zone. And this is the area specifically within these two seismic reflectors where I'm focusing my research and where I ran my attributes. So I'll talk a little bit about the workflow and methodology now. I start with the seismic data and then pick the seafloor and BSR surfaces and then convert to the usable format for my software and then crop the data to these parameters. Just so I was really focused on the gas hydrate stability zone. And then the majority of my time I spent calculating attributes and analyzing their responses, especially since these attributes have not been applied to gas hydrates before. I really wanted to take a lot of care to describe those results really, really thoroughly. Skewness and kurtosis were calculated through spectral decomposition methods. And then my supplemental attributes were calculated through single trace calculations in the software that I use. And then I implemented unsupervised machine learning, and I'll talk about that in just a minute. So again, I mentioned the spectral attributes, skewness and kurtosis. These measure the change of the shape of the seismic spectrum. And then the supplemental attributes are instantaneous frequency, sweetness, RMS amplitude, and envelope. These attributes are related to features like thin bed tuning, hydrocarbon accumulation or sweet spots, amplitude variation, changes in morphology, porosity, and hydrocarbon accumulation. So even though these might not specifically relate to attenuation itself, these attributes have been used in the Pegasus Basin before, especially for highlighting those weak BSRs. And I wanted to see if I could just compare the response for the spectral attributes to some of these more classical hydrocarbon related attributes. Okay, and now for unsupervised machine learning. Unsupervised basically means that the user doesn't have a ton of input into this type of machine learning, but there are parameters that are user defined, which I'll describe in a minute. The type of machine learning that I chose is self-organizing maps. This had been used in a study on the Pegasus Basin before, and it's a fairly simple and straightforward method of machine learning. It has often been classified as a clustering technique, but I believe it's more properly described as a dimensionality reduction technique, as it takes a certain higher number of input dimensions of data, determines the relationship between those data points in a manifold that's deformed to fit the data better, and then projects the output onto a lower, often two-dimensional space. And it's also thought of as a projection technique. So for my situation, I took all 6 of my input attributes, put them into the software that I was using. The algorithm ran, and in a couple minutes I had my main projections of the data that when you color with a 2D color map gives you these nice different clusters that you can relate to different geological or geophysical properties of your data. So for the SOM implementation, I had two different cases, case 1 and case 2. So for case 1, I implemented the SOM over this entire cropped window right here. So from the ocean bottom to even below the BSR. So it covered the entire gas hydrate stability zone and then below the BSR as well. The parameters that I was able to define are training iterations, decimation, and then number of classes. And for case 2, I wanted to reduce the facies or reduce some of this background facies clustering and really just focus on the gas hydrate stability zone and really ignore whatever was happening below that because it wasn't the focus of the project. So the only difference was that I ran the SOM between the ocean bottom and the BSR horizons. So for both of these, I implemented them over the full far and near angle stacks on my seismic survey. So I had basically 3 different results for SOM case 1 and 3 different results for SOM case 2. And I'll show those in a few slides. So now for some of the results and discussion. First of all, I wanted to better characterize my attribute results. So I described these attributes across 4 different zones. So zone 1 consisted of the ocean bottom and a series of relatively low amplitude, fairly continuous horizontal seismic reflectors below that. And then zone 2 consisted of some parallel here to subparallel, slightly wavy reflectors that may correspond to sediment waves that were described in this study here on the Pegasus Basin. And then within zone 3, these were fairly continuous horizontal to subhorizontal seismic reflectors that had a thicker bedded expression than in zone 1 or 2. Then zone 4 was the BSR and below that. So based on the studies from the Pegasus Basin, we expect that the lithology to be pretty fairly homogeneous throughout. Okay, so these are the results from the far and near angle stacks. The main takeaway here is that the near angle stack has a higher frequency content than the far angle stack, which will give some slight variation in the resolution of the data and then the response for the spectral attributes. Okay, here are the results for skewness. This is the the full angle stack. Positive skewness is this bright red color and negative skewness is the blue. So if we take a look at this per zone, we have in zone 1, primarily strong positive skewness, especially stronger over here towards what's called the Hikurangi Trough or Hikurangi Channel. And within zone 2, we see some mixed low positive to medium negative skewness in this, especially in this subparallel wavy sediment reflector zone. And then within zone 3, we see predominantly negative to, predominantly positive to strong positive skewness, especially where we saw this high amplitude BSR. So zone 3 is where we're particularly interested in for these attribute responses. And so I want to talk about this a little bit. We know that because we have a BSR, the BSR is formed when we have this contrast between hydrates and trapped free gas below it. The gas is trapped because the hydrates are relatively solid and permeable. So if we didn't have a BSR, that would be an indication that we didn't have hydrates. But because we do have a BSR, we're very, very confident that there are hydrates at some point within this interval of the gas hydrate stability zone. So where we see then this very strong positive skewness, that means our data is skewed toward the left. So those low amplitudes, or the lower frequencies of our data. And this is indicating that we have more attenuation of the higher amplitudes or the higher frequencies throughout this zone. So this is likely due to hydrate accumulation attenuating our data throughout the zone here. If we take a look at the results for the far angle stack and the near angle stack, we see generally the same trends, but we are able to observe the impact of the frequencies more now on our data. So in the near angle stack, we saw in the seismic line that we had higher frequency content there. So if we have more of those higher frequencies, those are going to be more toward the right on the seismic spectrum. So your data is going to be more skewed toward the right, which is negative skewness. So you're seeing where we saw some negative skewness in the full stack, that zone is more negative in general within the near angle stack than it is within the far angle stack or the full stack. On top of that, we have this entire zone 3 is much more positive skewness compared to zone 3 in the near angle stack, but we still have the general trends preserved between the far and near angle stacks. So that was something pretty interesting that I just wanted to point out. So now taking a look at the spectral kurtosis, this is the full stack, and the yellow colors are positive kurtosis, and then the blue, bright blue colors are negative kurtosis. So when we take a look at this per zone, just like we did for the skewness, we see within zone 1 that it's strong negative with a little bit of stronger positive, especially over towards the Hikarangi channel. Then zone 2 is almost entirely mixed low negative to negative kurtosis. And then within zone 3, we see strong positive kurtosis directly above the BSR. And then where the BSR was weak or discontinuous, we saw negative kurtosis. So similar to skewness, zone 3 is particularly interesting for our studies. Again, this strong positive kurtosis is directly above the strong BSR, which is a very good indicator that hydrates are present above the BSR. So this positive kurtosis then is likely due to hydrate accumulation in this area. And where we see a lot of negative kurtosis, that's indicating that we have fewer outliers in our data, possibly a broader spectrum of frequencies, and likely that means we don't have hydrates attenuating anything throughout this zone. And another thing I wanted to point out that I thought was interesting as well is that when we compare the response from these attributes, the spectral attributes in particular, to what we saw within the seismic data, we generally didn't see a ton of variations in amplitude, except within zone 2, where we saw some of those wavier, higher amplitude sediment reflectors. But this strong positive kurtosis here doesn't really correspond to any feature that really stands out to us in the amplitude spectrum. So in that sense, it helps us tie it to, this is probably gas hydrates and not just geologic or something related to the underlying geology or lithology of the area. Okay, so now taking a look just briefly at the results for the far angle stack and the near angle stack for the seismic. In the far angle stack, we see much more of those positive kurtosis responses, similar to how we saw in the skewness. And what was really interesting to me was that in the near angle stack, it's almost entirely negative kurtosis. So this is just likely to having a lot more of those higher frequencies gives us a bigger range of frequencies. So we have just more of that negative kurtosis showing up in the near angle stack than in the far angle stack. Okay, now we're going to take a look at the results and discussion for the self-organizing maps machine learning case. And I don't want to spend too much time on the histogram, but this color map, it will make more sense when I show the SOM results. But basically, I had 4 different facies or clusters kind of described in my SOM results. So the first was the variable frequency facies. This corresponded to a lot of the attenuation related responses that I saw in the spectral attributes. These kind of green colors are the mixed siliciclastics, or just the majority of the data, the background facies. The BSR and ocean bottom facies are these magenta colors. And then those possible sediment wave facies are these yellows and some tan beige colors. So then we had those different facies described based on what we saw in attributes and the seismic. So now let's look at the SOM itself. So we can look at this per zone, and we see that within zone 1, the ocean bottom and its corresponding reflectors, as well as the BSRs, are classified within this ocean bottom BSR facies, this magenta color. And those are really the only two seismic reflectors that are classified by that, besides some of these areas below the BSR. Then the rest of zone 1 is primarily these mixed siliciclastic facies, and then some of the variable frequency facies, where we saw some slight variations in skewness and kurtosis described earlier. Then within zone 2, where we saw those wavier subparallel sediment reflectors, those high amplitude reflectors, those are classified by the sediment wave facies. And then within zone 3, this is where we see the most of the variable frequency facies classified, especially above the BSR, which is what we would expect based on the results from skewness and kurtosis. So now if we take a look at the far angle stack versus the near angle stack, the variations between these angle stacks wasn't super significant, but I did want to point out a couple things. First was that we see better resolution of the sediment wave facies described in the near angle stack. Again, this is likely due to the underlying frequency content of the near angle stack compared to the far angle stack. And there's also slightly better clustering of those variable frequency facies in zone 1. And it's hard to tell if it's better in zone 1 or zone 2, but the key takeaway for SOM case 1 is that the attenuation effects were observed mainly in zone 3, and this is where we saw the most attenuation in our spectral attributes. So this is pretty much what we would expect. Now for SOM case 2, this was the SOM case that I computed between the ocean bottom horizon and the BSR. So we see per zone now generally more of these attenuation or variable frequency facies. We observe that even more now in zone 1 and again in zone 3. Zone 2 is still classified mainly as those mixed siliciclastic background facies and some of the sediment wave facies here throughout. And then in zone 3, you see mostly the variable frequency facies above the high amplitude BSR, and then some as well over here. Where the BSR was weak or discontinuous, low amplitude, above that we saw more of those mixed siliciclastic facies. Then for the far and near angle stacks, for SOM case 2, the near angle stack did a little bit better at highlighting some of those sediment wave facies within zone 2, and then there was slightly better relationship between the variable frequency clusters in zone 3 as well. So the key takeaway for this is that there was better discrimination between clusters compared to SOM case 1. So a few more conclusions as I wrap up. The first research question I had, just tying back to the beginning, was can skewness and kurtosis measure attenuation within the gas hydrate stability zone? So first of all, we saw that the results from attribute analysis show that the spectral attributes can highlight increasing attenuation throughout a likely hydrate saturated zone within the gas hydrate stability zone. These locations correspond to where we saw some high attenuation described in Claremont et al. In a few of his different seismic lines that he showed. Furthermore, since these spectral attribute responses in zone 3 do not correspond to any noticeable variations in the seismic amplitude line or the supplemental attributes, we conclude that it is related to gas hydrates and attenuation rather than changes in lithology. Additionally, based on these attribute responses, it appears that the hydrates in the Pegasus Basin are discontinuous throughout the gas hydrate stability zone. And finally, similar to other direct hydrocarbon indicators, spectral attributes may be used as a risking tool or as an indicator of some underlying feature. So direct hydrocarbon indicators are not 100% definitive in themselves. Flat spots have been drilled before and weren't actually economic. So it's not like a 100% yes, there is hydrocarbons here, but it's a tool that geoscientists use to better understand what's going on. And when you compound multiple DHIs, that gives you a lot more confidence that you're going to find something economic within the area. So I believe that these attributes would be useful if applied in that way, based on some of the results from this study. For my research question 2, which was, can machine learning enhance attenuation related responses in the gas hydrate stability zone? We saw that based on the SOM results, there was a corresponding result at the areas where the spectral attributes showed peak responses or variations. This indicates that the machine learning was able to slightly enhance attenuation features, although a combination of other spectral or statistical attributes such as slope or bandwidth or maybe roughness would likely increase this effect. As I mentioned, I had 4 attributes that I wasn't able to show just for sake of time that were not related to attenuation specifically. So if I had 6 attributes instead of just 2 that were related to attenuation, I think that would likely increase those attenuation responses than machine learning. And then when I compared the 2 SOM cases, it is observed that running machine learning between a smaller interval allows for more discrete classification of the data, and it's therefore recommended to calculate attributes and machine learning implementation across a narrower user-defined window or cropping horizons. I always like to have a few words on recommendations for future work. I feel like the work is never completely done as a researcher, so some things that I have been working on are synthetic seismics to really tie what I'm seeing in my seismic data to well data, since there isn't well data within the Pegasus Basin, unfortunately. I have been working on some synthetic well data and seismic data to try to make some relations there, but that proved to be a little bit more complex than I was prepared for. And I think it will take entire forward modeling to really get the responses that we want. So I'm hoping someone else at OU picks this up after I graduate, but that's something that would really be useful in this setting. Other things that I recommend for future work are using these spectral attributes to enhance the BSR. The BSR wasn't specifically the interest of my research, but it has been analyzed by many other researchers, and I think it would be interesting to see whether or not these attributes specifically can highlight some of those BSR features. And then comparing attenuation within gas hydrates to attenuation within pre-gas, seeing if these attributes can discriminate that at all. This research was funded by an ACS PRF grant, so very grateful for that. My data is available through the New Zealand Government Petroleum and Minerals Department, and then I ran almost all of my attributes using the ASPE software that is available here at the University of Oklahoma, and then I used Petrel as well. Would love to thank my committee, a lot of different people that have helped me through this research. I know they're not here today, but had a lot of help throughout this and wouldn't have brought all the work done without my talk today and for allowing me to present. And please do feel free to stay in touch. My email is there. If you have any questions you think about later about gas hydrates, feel free to reach out. So thank you so much.